A dark, frozen world holds secrets that shattered our solar system. Far beyond Neptune, drifting in the desolate scattered disk, orbits the dwarf planet Eris. It is larger and more massive than Pluto, a fact that alone forced astronomers to rewrite the rules of what makes a planet. This remote sentinel, discovered in 2005, became the center of a cosmic controversy. But that debate was just the beginning. Eris is a vault of enigmas, a place of extreme cold and profound isolation where every answer we find only reveals deeper, more baffling questions. By the end of this journey, you will uncover the 25 greatest unexplained mysteries locked within this icy sphere and its mysterious moon, dysnomia. How does a world so distant shine like a cosmic mirror? What catastrophic event threw it onto such a wildly tilted path? We are traveling to the absolute edge of our known celestial neighborhood, to a realm where darkness is not empty but full of whispers. What do you think is waiting for us in that endless cold? That brilliant shine is our first great puzzle. Eris possesses one of the most reflective surfaces we have ever seen in the outer solar system, a quality known as its albedo. It reflects about 90% of the sunlight that reaches it, which is a staggering amount. To understand how unusual this is, picture fresh snow on a clear winter day. That snow is bright, reflecting perhaps 80% of the light. Eris is brighter. It outshines even the brilliant, icy moon Enceladus. This makes it a dazzling beacon in the profound darkness of the scattered disk, a cosmic mirror floating in the void. But this creates an immediate and profound mystery. Eris is ancient. It has been orbiting in that deep freeze for billions of years, subjected to a relentless rain of cosmic radiation and tiny, high-speed impacts from space dust. This kind of bombardment should have darkened its surface significantly. Radiation, in particular, works like a cosmic tanning bed, breaking down complex ices and creating a dark, reddish, tar-like substance called tholins. We see this darkening on many other distant worlds, like Pluto's darker regions. So why does Eris look so pristine? The leading theory points to a process of surface renewal. The volatile ices on its surface, primarily methane and possibly nitrogen, might be constantly refreshing themselves. One possibility is that Eris has a very tenuous seasonal atmosphere. When it swings slightly closer to the Sun during its extremely elongated orbit, these surface ices could warm just enough to sublimate, turning directly from solid to gas. This gas might then travel to colder areas and refreeze, essentially repainting the surface with a fresh, bright coat of frost. Another, more dramatic idea involves geological activity. Could internal heat from radioactive decay or the gravitational squeeze of its moon be causing these ices to well up from below, covering older, darker material with new, brilliant ice? Yet each explanation raises new questions. The seasonal model requires a delicate balance we have not directly observed, and geological activity on such a small, cold world seems almost paradoxical. How does a dwarf planet so far from the sun's warmth manage to keep its face so clean? This is not a trivial detail. That blinding whiteness is a direct challenge, a sign that Eris is not a dead, static rock, but a world with ongoing processes we do not yet understand. The very thing that makes it easy for our telescopes to see, its shine, is the first clue that what we are looking at is far stranger than it appears. That pristine, icy surface holds another secret, one that makes Eris even more of an outlier. When we peer at it with spectrometers, instruments that break its light into a chemical fingerprint, we find the signature of frozen methane. This is expected for such a distant, cold world, but there is something conspicuously missing, or at least hiding. Where is all the nitrogen? This is the second great mystery. On Pluto, another large dwarf planet in the Kuiper belt, we see vast plains and glaciers of nitrogen ice. It is a dominant feature. Given their similar sizes and locations, astronomers fully expected Eris to have its own substantial reservoir of nitrogen, likely buried beneath its bright surface or spread across it. Yet the data tells a different story. The nitrogen we do detect on Eris is scarce and it seems fleeting. It is not forming stable, extensive ice sheets. So where did it all go? One possibility is that Eris simply lost it. Its orbit is far more elongated and tilted than Pluto's, taking it on a wild journey that swings it from about 3.7 billion to over 9.7 billion miles from the Sun. This extreme variation in solar heating could have triggered a process of runaway sublimation. Over billions of years, as Eris swung closer to the Sun during its long year, the volatile nitrogen ice may have warmed just enough to turn directly to gas and escape its weak gravity entirely, vanishing into space. Pluto, with its more circular and stable orbit, could have held onto its nitrogen. Another, more intriguing idea is that the nitrogen is still there but locked away. Perhaps it exists in a vast, global ocean deep beneath the icy crust, sealed in by a thick layer of harder water ice and methane clathrates. Or maybe it is trapped in a strange, glassy state within the ice itself, invisible to our remote sensors. The scarcity we see could simply be because the surface conditions are just wrong for nitrogen to condense and stay put. Each scenario paints a dramatically different picture of Eris's interior and history. Is it a world that bled its lighter elements into the void, becoming a purer, denser remnant of its former self? Or is it a world with a hidden, sloshing heart, a secret ocean kept liquid by internal heat and the strange chemistry of extreme pressure? The missing nitrogen is not just an absent ingredient. It is a clue to a planetary-scale story of loss, survival, and transformation, written in elements we cannot directly see. This brilliant, nitrogen-poor world follows a path unlike any other. The third mystery is not about what Eris is made of, but the wild, lonely road it travels. While most planets and major objects in our solar system orbit in a relatively flat disk called the ecliptic plane, Eris is a renegade. Its orbit is tilted at a staggering 44 degrees. Picture a spinning plate on a table representing the orderly orbits of the planets. Now imagine a coin launched from the edge of that plate, spinning off at a sharp angle into the air above. That coin is Eris, a world that moves dramatically above and below the solar system's main traffic lanes. This extreme inclination places it far outside the main population of the Kuiper belt, making it a true outlier in its own neighborhood. So how did it get there? Something with immense gravitational power must have grabbed this dwarf planet and hurled it onto this tilted path. One of the leading theories points to the gravitational influence of Neptune in the early, chaotic days of the solar system. As the giant planets migrated and jostled for position, their powerful gravity could have acted like a cosmic slingshot, flinging smaller objects like Eris into these strange, detached orbits. This process likely scattered many objects into what we now call the scattered disk, of which Eris is the largest known member. But some astronomers wonder if Neptune's influence alone is enough to explain such an extreme tilt. This leads to a more tantalizing possibility, the potential existence of an unseen, massive planet still lurking in the outermost dark. This hypothetical world, often called Planet 9, is theorized to be several times more massive than Earth, orbiting far beyond Pluto on a long, slow path. The gravitational pull of such a hidden giant could be shepherding the orbits of distant objects like Eris, aligning them in these peculiar, highly inclined paths. It is a ghostly hand shaping the dance of the outer solar system from the shadows. There is also the possibility of a more ancient and violent origin. Could Eris have been a wanderer from another star system, captured by our Sun's gravity in the distant past? Or was it involved in a colossal collision, a catastrophic event that not only altered its spin but sent it careening onto this unique trajectory? Its moon, Dysnomia, might be a remnant of such an impact. Each of these explanations points to a turbulent history written in the silent geometry of its path. The extreme inclination of Eris is more than an orbital curiosity. It is a fossil record of gravitational violence, a lasting signature of the dynamic and often destructive forces that shaped our solar system's outer frontier. This tilted path is a direct line of inquiry, pointing our gaze even further into the dark, asking what else might be out there, still unseen, that can move worlds. This languid spin leads us directly into our fourth great mystery. While most worlds in our solar system whirl with a certain youthful energy, completing a full rotation in a matter of hours, Eris seems to move in slow motion. Determining its exact rotation period has been a challenge for astronomers, given its immense distance and lack of clear surface features to track, but the best estimates we have are startling. Eris may take more than 25 hours, perhaps even close to a full Earth day, to turn just once on its axis. For a world of its size and mass, this is an extraordinarily slow, almost lethargic pace. Consider the other dwarf planets. Pluto spins once every 6.4 Earth days, a slow dance dictated by its large moon Charon, as they are tidally locked in a mutual embrace. Haumea, by contrast, is a frantic spinner, whirling so fast it has been distorted into an elongated shape. Eris sits in a strange middle ground, rotating too slowly for its size to be a simple consequence of its formation. So what put the brakes on this distant world? One compelling theory points to a colossal impact in the ancient past. A massive collision, perhaps the very same event that created its moon Dysnomia, could have delivered a staggering blow, sapping a tremendous amount of its original rotational momentum. Think of it like striking a spinning top with a hammer. The top would wobble and slow dramatically. If the impact was off-center and powerful enough, it could have literally knocked the spin out of Eris, leaving it with this prolonged day. Yet there is another force constantly at work, the gravitational pull of Dysnomia. Tidal forces from a moon can act as a brake over astronomical timescales, gradually synchronizing a planet's rotation with its moon's orbit. This is how Earth is slowly transferring its rotational energy to the moon, lengthening our own day by milliseconds each century. But Dysnomia is relatively small compared to Eris. For it to have slowed Eris's spin to such a crawl, the tidal interaction would have to be unusually strong, or Dysnomia would need to have once been in a much closer orbit. This suggests a complex and evolving gravitational relationship we do not yet fully understand. Could there be another unseen factor at play? Perhaps the internal structure of Eris, with a possible subsurface ocean, creates a kind of friction against the outer shell, acting as a hidden brake on its rotation. Or maybe its slow spin is a primordial relic, a sign it formed from a cloud of material that simply never had much spin to begin with. The languid rotation of Eris is a silent clock, ticking off a history of either immense violence or profound gravitational patience. Each slow turn asks us, was this world struck by a cataclysm, or is it locked in a slow, deep dance with its moon that we are only beginning to perceive? The name Eris itself is a declaration of discord chosen for the chaos it brought to astronomy, but its moon, Dysnomia, carries a meaning just as pointed. In Greek mythology, Dysnomia is the daughter of Eris, the spirit of lawlessness and civil disorder. This naming convention, however, was almost very different, and that near miss reveals our fifth great mystery, one woven from politics, pop culture, and a quiet rebellion within the scientific community. Before the official names were bestowed, the Discovery team had affectionate nicknames for the new world and its companion. They called the dwarf planet Xena after the television warrior princess, and its moon Gabrielle, her loyal companion. This was not just whimsy, it was a clever, subversive act. At the time, the International Astronomical Union had not yet defined what a planet was, and the discovery of this large, distant object was a direct challenge to the status quo. By nicknaming it Xena, the discoverers were essentially declaring they had found a 10th planet, a new warrior entering the solar system's arena. The names were a placeholder, but they carried the excitement and controversy of the moment. When the time came for official designations, the rules required names from creation mythology for dwarf planets, and so Xena became Eris, the goddess of strife. Her moon, following the tradition of being named for a figure related to the primary, became Dysnomia. On the surface, this seems like a neat mythological package. Yet the choice of Dysnomia, lawlessness, is profoundly loaded. It can be seen as a direct commentary on the chaotic demotion of Pluto and the new, unsettled law of the solar system that Eris helped to write. It is a permanent, subtle protest etched into the official catalogue. This naming process encapsulates a lingering tension. How do we categorize these distant worlds? Are they planets, dwarf planets, or something else entirely? The community remains divided. For some, the demotion of Pluto was a necessary scientific correction. For others, it felt like an arbitrary dismissal driven more by politics than pedagogy. Eris, and by extension Dysnomia, sit at the heart of this unresolved debate. They are constant reminders that our maps of the cosmos are not just charts of objects, but reflections of our own definitions, our arguments, and our ever-changing understanding. The names are not merely labels, they are the first chapter in the story of how this world disrupted our celestial order, a story whose final page has yet to be written. The surface of Eris is a perfect, brilliant white, but that does not mean it is featureless. Our sixth mystery probes the possibility that this frozen world is not entirely dormant. Some astronomers studying subtle changes in its brightness over time have suggested the surface might be dotted with strange formations. They could be sublimation pits where volatile ices like methane have turned directly to gas and escaped, leaving behind shallow depressions. Or more thrillingly, they might be the faint signatures of geysers, signs of cryovolcanism where a slurry of water, ammonia, or methane erupts from beneath the crust. Picture the dramatic plumes of Saturn's moon Enceladus, but on a world 10 times farther from the Sun. The evidence is not yet conclusive. It is a whisper in the data, but it is a compelling one. It points to localized geological activity, to places where the interior of Eris is still speaking to the surface, and that raises a profound question. Where is the heat coming from? At such an immense distance, the Sun is little more than a bright star, providing no meaningful warmth to power geological processes. The engine must be internal. One possibility is the slow, persistent decay of radioactive elements like uranium and thorium locked deep within its rocky core. Over billions of years, this decay can generate enough heat to soften ice and create movement. Another, more dynamic source could be tidal heating. As Eris and its moon Dysnomia orbit one another, their gravitational pull flexes and stretches their interiors. This constant kneading generates friction and heat, much like repeatedly bending a piece of metal until it becomes warm. This process is what keeps the subsurface ocean of Jupiter's moon Europa liquid. Could a similar, subtle tug of war be at work here, providing just enough energy to occasionally crack the icy shell and allow material to erupt? There is also the lingering heat from its own formation and from the colossal impact that may have created Dysnomia. That catastrophic event would have injected a tremendous amount of thermal energy into Eris, a warmth that could take eons to fully dissipate in the insulating vacuum of space. If any of these processes are active, they transform Eris from a simple frozen relic into a complex geological world. The potential for sublimation pits or geysers suggests a surface that is actively changing, a landscape where fresh, bright ice is being deposited or where dark material is being exposed. It hints at an interior that is not entirely frozen solid, but perhaps layered with a slushy mantle or even a hidden ocean acting as a reservoir for these eruptions. This mystery connects directly to the blinding albedo and the missing nitrogen. An active surface would explain how Eris stays so bright, constantly refreshed by new frost from within. And it could explain the fate of the nitrogen, perhaps locked away in that subsurface reservoir or violently expelled in ancient plumes. The search for these features is a search for Eris's pulse, a faint beat in the deep cold that tells us this distant world is still very much alive. The potential for a geologically active world leads us to a fundamental contradiction. Our seventh mystery is a paradox of mass and structure. We know Eris is remarkably dense for an object in the outer solar system. Precise measurements of its mass derived from the orbit of its moon Dysnomia and its size calculated from its brightness and distance give us a clear number. Eris has a density of about 2.5 grams per cubic centimeter. This is significantly higher than Pluto's density of about 1.8. What does this number tell us? It points to a world made not just of light, fluffy ices, but of a substantial amount of rock and metal. The high density suggests Eris is composed of roughly 70 to 80% rock, with the remainder being water ice and other frozen volatiles. In essence, it is more like a rocky planet coated in a thick mantle of ice rather than a giant snowball. This composition makes sense for an object that formed early in the solar system's history, accreting material from the primordial disk. But here is where the paradox emerges. An object of this size and mass with such a large rocky core should have experienced significant internal heating during its formation. The energy from countless collisions and the decay of radioactive elements in all that rock should have melted the interior. This process, called differentiation, would have caused the heavy rock and metal to sink to the center, forming a distinct core, while the lighter ices rose to form a mantle and crust. A differentiated body often retains enough internal heat to drive geological activity for billions of years, like the volcanism we see on some moons. Yet, the surface of Eris, while possibly active in subtle ways, does not show the widespread dramatic signs of such a warm and dynamic history. Where are the vast resurfaced plains? Where are the clear tectonic features or massive cryovolcanic constructs? The evidence we have suggests a world that is largely geologically quiet. So why does a world built like a rocky planet act like a frozen, dormant one? One possible resolution lies in the idea of porosity. Perhaps the rock inside Eris is not packed into a solid, dense sphere, but is instead a loose, rubble pile structure with vast gaps and voids. This would lower the effective density without requiring less actual rock, and it would also act as a superb insulator, trapping any internal heat and preventing it from reaching the surface to drive geology. Eris could be a cosmic thermos bottle, warm inside but frozen solid on the outside. Another possibility is that the rock-to-ice ratio is even more extreme than we think. If Eris is almost entirely rock with just a thin shell of ice, then there simply may not be enough volatile material to create the kind of icy geology we are looking for. The activity might be there, but locked deep within a stony interior, invisible to us. Or perhaps the heat was there and was used up long ago in a brief, violent period of activity that completely resurfaced the world, leaving behind the pristine, bright shell we see today. The mass discrepancy paradox forces us to question our basic models of how these distant worlds are put together. Is Eris a tightly packed, differentiated world hiding its heat, or a fragile, porous aggregate that never fully melted? The answer reshapes our understanding of what can exist in the frozen dark and how much life, in a geological sense, a world can hold onto across the eons. That dense, rocky core sits at the center of a journey of staggering extremes. Eris follows not a gentle circle around the sun, but a stretched and elongated ellipse, a path so exaggerated it defines the very nature of its existence. This highly elliptical orbit is our eighth mystery, a celestial roller coaster that subjects this world to the most dramatic climate swings imaginable in our solar system. For 558 Earth years, Eris completes one slow, loping circuit. At its farthest point, a place called aphelion, it drifts over 9.7 billion miles from the sun. a distance so vast our star is reduced to little more than an exceptionally bright point of light. The temperature here plunges to a mere 30 degrees above absolute zero. At this cold, chemistry almost grinds to a halt. Then, over centuries, it begins the long fall inward. At its closest approach, perihelion, it swings to within about 3.7 billion miles of the Sun. While still unimaginably cold by our standards, this proximity brings a relative warmth, with surface temperatures possibly climbing to a balmy -350 degrees Fahrenheit. This 60-degree swing may sound minor, but in the realm of frozen volatiles, it is the difference between a permanent deep freeze and a fleeting summer. This cyclical thaw triggers a breathtaking planetary process. Astronomers believe Eris possesses a transient, seasonal atmosphere. As it nears perihelion, the slight increase in solar energy is enough to cause the frozen methane and possibly nitrogen on its surface to sublimate, turning directly from solid to gas. For a brief period in its multi-century year, a whisper-thin envelope of gas may cling to the world. Then, as it journeys back into the deep freeze, this tenuous atmosphere must freeze out entirely, snowing back down onto the surface in a fresh, bright layer of frost. This is the likely engine behind its brilliant reflectivity, a global resurfacing event that happens just once every 5.5 centuries. But the exact mechanics of this freeze-thaw cycle are deeply puzzling. How uniform is this process? Does the atmosphere collapse all at once, or does it retreat to the coldest polar regions first, creating temporary atmospheric rivers that flow across the landscape? The physics of an atmosphere freezing directly onto a surface in such a weak gravitational field is something we have never directly observed. It might create exotic snows with textures and structures unlike anything on Earth. These wild temperature swings also pose a profound question for any potential geological activity. Could the periodic warming at perihelion be enough to trigger cryovolcanic eruptions as subsurface pockets of volatile slush expand and seek release? Or does the intense cold at aphelion seal the world in a state of suspended animation, locking away its secrets under a thickening layer of absolute zero ice for centuries at a time? This orbit makes Eris a world of two starkly different faces, a dormant ice ball for most of its long year that briefly, almost imperceptibly, stirs to a semblance of climatic life. Its entire geological rhythm is dictated by this slow, cosmic heartbeat, a pulse measured not in beats per minute, but in degrees per century. The elliptical path is not just its road through space, it is the master clock for every possible process on its surface, a timer set for changes no human has ever witnessed. The stark contrast between Eris and its moon is a puzzle in plain sight. While the dwarf planet gleams like a cosmic mirror, Dysnomia is a shadowy companion, reflecting only about 5% of the sunlight that reaches it. This is our ninth mystery, a question of shared origins and separate fates. Why would a moon orbiting so close to a brilliant, ice-covered world be cloaked in such profound darkness? They share the same environment, bathed in the same weak sunlight and bombarded by the same cosmic radiation. Yet one is pristine white, the other nearly black. This dramatic difference suggests their surfaces are made of fundamentally different stuff. Dysnomia's darkness points to a composition rich in carbonaceous material, complex organic compounds that have been heavily processed by radiation over billions of years. It is the color of cosmic soot, the end product of a long, slow cooking under the harsh rays of space. One immediate possibility is that Dysnomia formed from different material than Eris. In the chaotic early solar system, the disk of debris from which they coalesced might have been chemically segregated. Perhaps Eris formed closer to the center of a local cloud where cleaner water and methane ice dominated, while Dysnomia accreted from darker, carbon-rich material from the outer edges of that same cloud. This would make them siblings from the same family but with distinct genetic inheritances. A more dramatic and widely held theory involves a catastrophic collision. If dysnomia is a fragment from a giant impact on Eris, as many astronomers believe, its dark surface could be a glimpse into the interior of the dwarf planet. The impact could have excavated material from deep beneath Eris's bright icy crust, hurling a chunk of its darker, rocky core or a layer of radiation-processed mantle into orbit. In this scenario, dysnomia is not a separate world captured by gravity, but a piece of Eris's own hidden heart, now orbiting its parent as a permanent reminder of that ancient violence. Its darkness is the true color of Eris beneath the frost, yet another factor is the relentless power of space weathering. Without an atmosphere to protect it and lacking any internal process to refresh its surface, dysnomia is completely exposed. Micrometeorite impacts and constant cosmic radiation would have long ago darkened any bright ices on its surface, baking them into a dark, carbonaceous crust. Eris, with its potential for seasonal resurfacing or geological activity, can fight this process. Dysnomia, smaller and likely geologically dead, cannot. It has simply aged differently, its face permanently scarred by the unshielded environment of deep space. This simple observation of color forces us to reconsider the relationship between these two bodies. Are we looking at a captured alien object, a piece of Eris's interior, or just a world that has weathered the eons without the means to heal itself? The darkness of dysnomia is not an absence of light, but a presence of history, a silent story written in the chemistry of its ancient, unreflective surface. The dark companion dysnomia casts a long shadow, but even the brilliant surface of Eris itself holds a subtle, colorful secret. This 10th mystery focuses on a specific ingredient in its icy makeup, the reddish-tinged methane ice that paints its landscape. We know methane exists there, frozen solid, but its color is a clue to a complex history. On other worlds, like Pluto, methane ice is often whitish or gray. On Eris, it carries a distinct reddish hue. Scientists point to a simple, relentless process, irradiation. As cosmic rays and solar particles bombard the surface over eons, they break apart the simple methane molecules. This radiation chemistry forces the carbon and hydrogen to recombine into longer, more complex chains, creating reddish-brown organic compounds called tholins. It is a cosmic tanning process, slowly darkening and reddening the ice. Yet here is the puzzle: the redness appears surprisingly consistent across the surface of Eris. This uniformity is strange. If radiation is the sole artist, we would expect a patchwork. Areas that face the sun more directly, or regions shielded by topography, should show different levels of processing. The poles, which might experience less direct irradiation over long periods, should look different from the equator, but the data suggests a more even, global tint. This forces us to question the simple story: is the radiation exposure somehow uniform across the entire world? That seems highly unlikely given its slow rotation and tilted axis. Or is something else actively mixing and redistributing this colored material? One possibility is that the reddish tholins are not just sitting where they formed. They could be incredibly fine dust, lifted by the tenuous seasonal atmosphere and carried by weak winds to settle evenly across the globe, painting every crater and plain with the same rusty brushstroke. This would require an active atmospheric cycle far more effective than we currently imagine. Another, more profound idea is that the redness is not just a surface stain, but an ingredient. Perhaps these complex organic molecules are being created not only on the surface, but within the ice itself, or even delivered from below. If Eris has internal geological activity, however subtle, it could be bringing up material from a reservoir where these tholins have been cooking for billions of years. The consistent color might then be a sign of a globally mixed crust, churned by slow convection or impacted by countless micrometeorites over time. It could even hint at the presence of other, more exotic ices mixed with the methane, like ethane or propane, which undergo different coloration under radiation. The mystery of the red methane is not about the color itself, but what that color reveals about the world's activity. Is Eris a passive canvas slowly being tinted by the impersonal brush of cosmic rays? Or is it an active studio where internal processes and a whisper-thin atmosphere are carefully blending the pigments to create a uniform masterpiece of rusty ice? The answer lies in the shade of red, a subtle clue to whether this distant world is merely weathering the eons or quietly managing its own complexion. That subtle, rusty hue is painted by forces we can barely perceive. The 11th mystery takes us from the chemistry of the ice to the physics of the air, or more accurately, the ghost of an atmosphere that comes and goes. If Eris possesses a transient atmosphere, as many suspect, it would be a thing of wild extremes, a breath that freezes solid for centuries only to be exhaled in a fleeting, tenuous gasp. The theoretical surface pressure on this world would not be a stable number, but a roller coaster dictated entirely by its wild elliptical orbit. At aphelion, its farthest point, the entire atmosphere would likely have collapsed, frozen into a uniform layer of frost. The surface pressure would be effectively zero, a perfect vacuum against the ice. But as Eris swings inward toward perihelion, the slight increase in solar warmth could trigger a spectacular change. Frozen methane and nitrogen on the surface would begin to sublimate, turning directly from solid to gas. For a brief window in its 558-year orbit, a whisper-thin envelope of gas might form. The pressure would rise, but to what? Estimates suggest it might reach a maximum of just 1/1,000,000th of Earth's sea level pressure, perhaps even less. This is not an atmosphere you could breathe. It is more like the thin exosphere of our own moon, a collection of molecules so sparse they rarely bump into each other. The true mystery lies in how these extreme fluctuations would sculpt the surface. Think of frost forming on a cold window. On Eris, this process would be planetary in scale, but governed by a bizarre rhythm. As the atmosphere freezes out, where does the frost fall? Does it settle evenly, creating that globally bright surface we see, or does it accumulate in specific cold traps like permanently shadowed craters at the poles? The distribution of this frost would directly control the albedo, the reflectivity of different regions. Furthermore, the rate of sublimation, the speed at which ice turns to gas, would vary dramatically with both temperature and pressure. In the near vacuum of aphelion, any tiny patch of ice warmed by a random heat source would vanish almost instantly into space. But during the brief atmospheric period, the gas itself creates a buffer. Molecules leaving the surface would now collide with others in the thin air, some bouncing back down. This would slow the net loss of material, creating a more complex exchange between surface and sky. Could this lead to strange phenomena like temporary winds? Even the faintest breeze in such weak gravity might be enough to transport fine dust and dark Tholen particles, redistributing them and explaining the surprisingly uniform reddish tint. The puzzle for astronomers is modeling this dance without any direct data. We are trying to predict the weather on a world where the atmosphere itself is a seasonal event, where the air is a temporary film of vaporizing ices that might flow from warmer equatorial regions to colder poles before snowing out. How do you map the climate of a place where summer, such as it is, lasts for only a few decades out of centuries? These theoretical pressure variations are not just academic. They are the invisible hand that might carve subtle features into the ice, control the global paint job, and determine whether Eris's surface is a static monument or a slowly shifting canvas of frost and shadow. That whisper-thin atmosphere is a fleeting breath, but far beneath the frozen crust, a much more profound secret may be locked away. The 12th mystery asks a question that seems impossible this far from the sun. Could Eris hide a global ocean of liquid water? The very idea sounds like a fantasy. Surface temperatures here are hundreds of degrees below zero, a realm where water is harder than granite. Yet planetary science has taught us that cold alone cannot seal a world's fate. We now know that subsurface oceans are surprisingly common in the outer solar system, hidden beneath the icy shells of moons like Europa, Enceladus, and Ganymede. They are kept liquid not by the sun's warmth, but by internal heat, primarily from the steady decay of radioactive elements like uranium and thorium deep within their rocky cores. This radiogenic heat acts like a buried furnace, insulated by miles of overlying ice. Given Eris's high density and substantial rocky composition, it almost certainly possesses a significant reservoir of this long-lived radioactive material. The heat generated over billions of years could be more than enough to maintain a layer of liquid water at the boundary between its rocky core and its thick icy mantle. But viability is not certainty. The existence of such an ocean depends on a delicate balance between heat production and heat loss. The icy shell of Eris must be thick enough to provide superb insulation, trapping the warmth inside, but not so thick and rigid that it completely suppresses any geological expression of the ocean below. The presence of ammonia or salts, which act as antifreeze, could also dramatically lower the freezing point of the water, making a liquid layer far more likely. So, if this hidden sea does exist, how could we ever hope to detect it from across the solar system? Astronomers look for subtle gravitational and thermal signatures. One key signal would come from the precise shape of Eris itself. As it rotates, the centrifugal force causes it to bulge slightly at its equator. If the interior is entirely solid and rigid, this bulge would have a specific, predictable shape. But if a liquid layer separates the core from the outer shell, the icy crust can deform more easily, leading to a different, more pronounced equatorial bulge. By measuring Eris's shape with extreme precision, perhaps with a future spacecraft flyby, we could infer the internal structure. Another clue lies in the exchange of material between the ocean and the surface. On Enceladus, we see direct evidence of its ocean in the form of spectacular geysers erupting from fractures in the ice. If Eris has any form of cryovolcanic activity, or even just localized regions where the crust is thin, we might detect the chemical signature of ocean material, like salts or complex organics on its bright surface. Even the pattern of heat radiating from Eris could tell a story. An entirely frozen world would radiate heat in a relatively uniform way. A world with internal ocean dynamics might show subtle, localized warm spots where heat is being transported upward through the ice, perhaps along tectonic faults or plumes. For now, these are tantalizing possibilities, whispers in the data, yet the implications are staggering. A subsurface ocean on Eris would transform it from a simple frozen relic into a potential habitat, a dark, pressurized abyss where the basic ingredients for life, water, chemistry, and energy might coexist. It would mean that such hidden seas are not confined to the realms of giant planets, but could exist even on lonely dwarf planets adrift in the scattered disk. The deep cold of space, it seems, might not be a barrier to hidden warmth, but its perfect insulator. That potential for a hidden ocean rests upon a fundamental measurement, one that sets Eris starkly apart from its celestial cousin. The 13th mystery is a story told in numbers, a direct comparison that reveals a profound difference in their very essence. Eris is denser than Pluto, and not by a small margin. Our best estimates place Eris's density at about 2.5 grams per cubic centimeter. Pluto, by contrast, has a density of just 1.86. This is a significant gap. To understand what this means, picture two seemingly similar snowballs. You pick them up and one is unexpectedly heavy for its size. That heavier snowball has more rock packed into it, less fluffy ice. That is the story of Eris versus Pluto. Both are icy dwarf planets in the distant reaches, but Eris seems built from a fundamentally different recipe, one with a much higher proportion of rock and metal to ice. The immediate question is why? How could two large objects forming in the same general neighborhood of the early solar system end up with such different internal compositions? One leading theory points to their distinct histories of bombardment and collision. Perhaps Eris suffered a catastrophic impact early in its life, one so violent that it blasted away a significant portion of its original, lighter icy mantle, leaving behind a denser, rockier remnant. This would be like stripping the fluffy frosting off a cake, leaving a denser core exposed. Pluto, avoiding such a devastating strike, may have retained more of its primordial icy blanket. Another possibility involves their formation locations. While both reside in the Kuiper Belt region today, they may have been born in different parts of the primordial disk. Eris could have formed closer to the Sun, where temperatures were warmer and volatile ices like methane and nitrogen were less abundant, allowing it to accrete more rock relative to ice. Later, gravitational interactions with the giant planets could have hurled it out to its current distant orbit. Pluto, forming farther out in a colder, icier region, naturally incorporated more light material into its structure. There is also the factor of internal compression. Eris is more massive than Pluto. Its stronger gravity could be squeezing its internal materials more tightly, packing the rock and ice into a smaller volume and thus increasing its overall density. This effect might be more pronounced if Eris has a more differentiated interior with a compact, solid, rocky core. Pluto's interior might be more porous or less fully separated, leaving more empty space within its structure. This density discrepancy is not a minor detail. It forces us to reconsider the Kuiper Belt and scattered disk not as a uniform repository of similar icy worlds, but as a graveyard of planetary embryos with wildly diverse origins and histories. They are not interchangeable. Eris's greater density suggests it is a more mature, evolved, or simply luckier survivor of the solar system's violent infancy. It holds onto more of the heavy stuff, the primordial building blocks of terrestrial planets. This single number, 2.5, is a key that unlocks questions about everything from its internal heat to its surface geology. A rockier world has more radioactive material to generate warmth, supporting the possibility of that subsurface ocean. It also has a stronger gravitational anchor, which could affect how its atmosphere behaves and how its surface features form. The density of Eris is a quiet declaration. It tells us that in the darkness there is not just ice, but the bone and stone of a world that chose or was forced to keep its heavy heart. This rockier, denser world travels a path that defies simple chaos. For an orbit as tilted and elongated as that of Eris, stability is not a given, it is a profound puzzle. This is our 14th mystery, the unexplained endurance of its wild trajectory. In the gravitational pinball machine of the early solar system, objects on such extreme paths were typically either flung into interstellar space entirely or pulled inward to be swallowed by the giant planets. Yet Eris has persisted for over 4 billion years, tracing its lopsided loop above and below the plane of the planets. How did it avoid being scattered, ejected, or captured? Its survival suggests it found a safe harbor, a gravitational niche where the tugs of the known giant planets, particularly Neptune, balance out in a delicate and persistent way. This is not a random orbit, it is a protected one, a path that has been mathematically sculpted to avoid close, destabilizing encounters over cosmic timescales. Astronomers call this a stable resonance, a repeating gravitational rhythm. Eris's orbital period is likely in a precise ratio with Neptune's, meaning for every certain number of orbits Neptune completes, Eris completes a different number. This rhythmic dance ensures they never get too close, like two runners on separate tracks whose speeds are perfectly timed so they never collide. Neptune's gravity gives Eris a consistent, predictable nudge at the same point in its orbit every cycle, which over eons acts not to disrupt it but to shepherd it, locking it into this strange inclined path. But some scientists question whether Neptune's influence alone is sufficient to provide such long-term stability from such a great distance. This leads to the more tantalizing possibility of an unseen anchor. The hypothetical planet 9, a massive world thought to be orbiting far beyond Pluto, could be the architect of this stability. Its immense gravity, acting from hundreds of times farther than Earth is from the Sun, could be creating a vast zone of gravitational influence in the scattered disk. Within this zone, the orbits of objects like Eris are corralled and stabilized, their high inclinations and elongated shapes not being signs of chaos, but of order imposed by a distant, unseen master. Think of it as a deep, slow-moving eddy in a river current, a place where floating debris naturally collects and circles, protected from the main flow. Eris might be caught in just such a cosmic eddy, its path maintained by the gentle, persistent pull of a hidden giant. There is also the possibility that Eris is not alone in its peculiar orbit. It may be part of a population of objects all sharing similar orbital characteristics, a family of survivors that found the same stable niche. Their collective existence would reinforce the idea of a structured, rather than random, gravitational environment in the outermost dark. The stability of Eris's orbit is therefore a clue to the architecture of the solar system's frontier. It tells us that even in the apparent disorder of the scattered disk, there are rules, patterns, and perhaps even unseen sentinels maintaining a fragile balance. This world's enduring path is a map, and if we read it correctly, it may point directly to what else is waiting in the perpetual night. Dysnomia's dance around Eris may be hiding a fundamental clue about the nature of their bond. Our 15th mystery probes the gravitational relationship between this dark moon and its brilliant parent, specifically the question of tidal locking. In most planet-moon systems we see, especially with larger moons, the moon becomes tidally locked over time. This means the same face of the moon always points toward its planet, just as our own moon always shows Earth its familiar face. This lock is the result of gravitational tides, a constant tug that gradually slows a moon's rotation until it matches its orbital period. Given its size and proximity, Dysnomia is almost certainly tidally locked to Eris. But this expected lock, if confirmed, would itself be deeply unusual because of Eris's own languid spin. The process of tidal locking is a two-way street. While the moon's rotation slows, the planet's rotation is also being subtly braked by the moon's gravity. For a typical planet spinning quickly, locking a moon is a straightforward process. But Eris already rotates incredibly slowly. This means the gravitational tides between Eris and Dysnomia are exceptionally weak, operating on a timescale of profound slowness. For Dysnomia to have become locked to such a lethargically spinning world suggests either an ancient, powerful connection or a moon that formed already in a locked state from the debris of a colossal impact. If Dysnomia is not tidally locked, however, the implications are even more startling. A moon that still turns independently would imply a much younger system, or one where the internal structure of Dysnomia creates unusual friction, resisting the locking process. More importantly, a lack of lock would mean the tidal forces are not in equilibrium. This continuous flexing, as Dysnomia's gravitational pull moves across a rotating Eris, would generate internal heat through friction. This tidal heating could be a significant energy source, potentially helping to maintain a subsurface ocean within Eris or driving subtle geological activity on its surface. It would mean their gravitational dance is not a still portrait but an ongoing, warming embrace. So the simple yes or no of Dysnomia's lock is a direct window into the thermal engine of this distant system. A locked moon suggests a quiet, settled relationship where the major heating events are in the distant past. An unlocked moon hints at a dynamic present, with friction still cooking their interiors and possibly fueling the very processes that keep Eris's surface so brilliantly clean. This silent question of orbital synchronicity asks us to listen for the faint heartbeat of heat in the dark, a rhythm set not by the sun, but by the slow, patient pull of a dark companion on a world of ice. The silent gravitational lock between these two bodies whispers of a violent beginning. Our 16th and 17th mysteries are intertwined, probing the cataclysmic birth of the Eris dysnomia system. The leading theory is one of immense violence, a colossal impact in the ancient dark. Picture the early solar system, a crowded shooting gallery of planetary embryos. A proto-Eris, still forming, is struck a glancing blow by another massive object. The energy released is unimaginable, vaporizing rock and ice and hurling a vast cloud of debris into orbit around the wounded world. From this swirling disk of destruction, the fragments slowly coalesce, and the largest survivor becomes dysnomia, forever bound to its parent. This narrative mirrors the creation of our own moon, believed to have formed from debris after a Mars-sized object slammed into the young Earth. But here, in the frozen reaches of the scattered disk, the physics of such an event become deeply strange. The extreme cold changes everything. Ices behave differently than rock. They can shatter, melt, and refreeze in ways that alter the fundamental mechanics of the debris disk. How does a cloud of vaporized methane and water ice, in a place where the ambient temperature is near absolute zero, condense and clump together to form a moon? The timeline is also a puzzle. Did this happen in the first 100 million years of the solar system, when such giant impacts were common? Or was it a later, freak accident in an already thinning disk of material? The scale of the impactor required is another unknown. To create a moon as substantial as dysnomia relative to Eris, the impacting body would likely need to be a significant fraction of Eris's own size. This wasn't a pebble striking a giant, it was more like two worlds meeting in a catastrophic merger. Yet this leads to perhaps the most perplexing clue of all. Despite surviving what should have been a planet-shattering collision, Eris today is almost perfectly spherical. Major impacts often leave lasting scars, distorting a world's shape or triggering geological upheaval that creates massive, asymmetric features. Haumea, another dwarf planet, was likely struck so hard it was sent into a dizzying spin and stretched into an elongated ellipsoid. So why does Eris show no such obvious distortion? One possibility is that the impact was just gentle enough. A low-velocity, grazing collision might have lofted sufficient material to form dysnomia without completely disrupting Eris's internal structure, allowing its own gravity to slowly pull it back into a sphere over eons. Its high rock content and strong gravity would have aided this smooth recovery. Another, more intriguing idea is that the impact did not happen to a fully formed, solid Eris, but to a younger, warmer, and perhaps partially differentiated body. If its interior was still malleable, even slushy, the wound from the impact could have healed more completely, like a deep cut in soft clay that smooths over. The event may have even been the final act that fully differentiated its core and mantle. The spherical shape, then, is not proof of a peaceful history, but a testament to a world's resilience. It forces us to ask what we are really seeing. Is the pristine, bright surface of Eris the calm after an ancient storm, a global facelift performed by its own gravity in the aftermath of cosmic violence? The formation of this pair is a story written in missing pieces, a dramatic origin that somehow left behind a world of perfect, silent geometry. The chemistry of Eris' surface holds another subtle, telling clue. Our 18th mystery focuses on a specific and unexpected fingerprint in its icy makeup, the peculiar presence of ethane ice. When astronomers analyze the light reflected from Eris, they detect not only the strong signature of methane but also faint traces of ethane. This is a significant detail. Ethane is not a primordial ice you would expect to form directly from the solar nebula this far out. Instead, it is a product of radiation chemistry. When high-energy cosmic rays or solar particles slam into frozen methane, they break apart its simple molecules. The carbon and hydrogen atoms can then recombine into more complex chains, and one of the first and most stable products of this process is ethane. It is essentially a cooked version of methane, a sign that the surface has been irradiated for a very long time. Given the presumed intensity of the radiation environment in the scattered disk over billions of years, you would expect ethane to be a dominant feature, a thick, dark coating covering the landscape. Yet the data shows only trace amounts. The ethane signature is there, but it is surprisingly weak. This creates a puzzling contradiction. If radiation is constantly processing the methane, why hasn't it all turned into ethane and other, even more complex, tarry substances? One possibility is that the surface is being actively refreshed. The same seasonal or geological processes that keep Eris so brilliantly bright may also be burying or removing the ethane as it forms. Imagine a world where it constantly snows fresh, clean methane frost. This new layer would cover the older, radiation-processed ice, including the ethane, sealing it beneath a pristine blanket. Over time, the ethane could be buried deep within the crust or even recycled back into simpler molecules through further chemistry or heat. Another mechanism could involve the unique properties of the ice itself. On such a cold world, the surface ice might be incredibly porous, like a cosmic sponge. When radiation creates ethane, it might not stay on the surface as a distinct layer. Instead, it could diffuse down into the pore spaces within the ice matrix, becoming diluted and hidden from our remote sensors. Its chemical signature would be present but smeared out and less obvious. There is also the chance that the radiation environment at Eris is not as harsh as we assume. Perhaps its wild orbit and extreme distance provide some shelter, or its own magnetic field, though highly unlikely for a body of its size, could deflect some particles. But the most intriguing explanation points to an active chemical cycle. Could there be a process that reforms methane from ethane or other breakdown products? This would require an energy source and a chemical pathway, perhaps driven by internal heat or even by the seasonal freeze-thaw of its tenuous atmosphere. The faint whisper of ethane, then, is a delicate balance sheet. It tells us that radiation is indeed at work cooking the surface ices, but it also tells us that something else is at work too, a process of renewal or concealment that prevents the radiation from having the final word. The ice of Eris is not a passive record of bombardment, but an active ledger where creation and destruction are in a constant, quiet struggle. The absence of a tail is a glaring cosmic omission. For any world with a highly eccentric orbit and volatile ices, the journey near the sun is a moment of truth. As it swings through perihelion, the slight warmth should cause its frozen methane and nitrogen to sublimate, turning directly to gas. For a classic comet, this process creates a spectacular halo of gas and dust called a coma, and the pressure of solar radiation pushes that material outward into a long, luminous tail that can stretch for millions of miles. Yet Eris, despite completing this exact journey every 558 years, has never once been seen with a tail or even a faint coma. Our telescopes have watched, but the distant world remains a perfect, solitary point of light. This is the 19th great mystery, a question of missing plumes. If the ice is sublimating to create a transient atmosphere, as we strongly suspect, then where does all that gas go? Why doesn't it stream away to form the classic signature of an active icy body? One possibility is gravity. Eris, while small, is far more massive than any typical comet. Its gravitational pull, though weak, might be just strong enough to hold onto the majority of the gas molecules that boil off its surface. Instead of escaping freely into space to be swept into a tail, the gas may form a very thin, very tight, and gravitationally bound shroud that clings close to the surface. This would be less of a traditional atmosphere and more of an extended exosphere, a cloud so diffuse and close to the body that our current instruments simply cannot resolve it from the brilliant glare of the icy surface itself. Another, more dynamic explanation involves speed. The sublimation process on Eris might be incredibly slow and uniform, On a comet, sublimation often happens from specific sun-warmed jets or cracks, creating concentrated streams of gas that are easily pushed into a tail. On Eris, the sublimation could be a gentle global sigh. The gas emerges evenly from every sunlit patch of ice, creating no concentrated jets for the solar wind to grab onto. Without these focused sources, the material might simply diffuse outward in all directions, creating an imperceptibly thin cloud that dissipates almost as quickly as it forms. There is also a chilling third option, the role of temperature and recondensation. The environment around Eris, even at perihelion, is brutally cold. A gas molecule that escapes the surface might only travel a short distance before it recondenses, freezing directly back onto the icy crust as frost. This could create a rapid local cycle where gas is constantly being made and immediately recaptured, never achieving the critical density or velocity needed to form a detectable tail. The solar wind itself, the stream of charged particles from the sun that sculpts cometary tails, is also incredibly feeble at Eris's distance. It may lack the strength to push any escaping material into a distinct directional plume. The lack of a tail, therefore, is not proof of inactivity. It could be proof of a delicate and alien balance. Eris may exist in a state of perfect equilibrium, where its gravity, its cold, and the weak solar wind conspire to keep its volatile materials on a very short leash. Its atmosphere does not flow, it breathes in and out in a silent rhythm locked to its own surface. This missing tail forces us to redefine what activity looks like in the deep freeze. It tells us that the drama of the outer solar system is not always written in brilliant plumes and vast streams, but sometimes in the silent, stubborn hold of a distant world over its own fleeting breath. That silent breath of atmosphere may leave no visible tail, but it writes its signature in a spectrum of invisible light. When we peer at Eris, not just in visible light, but in the infrared, we see the chemical fingerprints of its surface ices in exquisite detail. Yet here, in the precise patterns of how those ices absorb infrared radiation, lies our 20th great mystery, a subtle but telling mismatch. The infrared absorption bands from Eris do not line up perfectly with the signatures we measure from pure methane or water ice in our laboratories here on Earth. It is as if we are listening to a familiar song, but the notes are slightly off-key. This discrepancy tells us that the ice on Eris is not in a simple, pristine state we can easily replicate. The precise crystalline structure of the ice, or the specific cocktail of ices mixed together, is something we have not yet fully deciphered. On Earth, water ice exists in the familiar form we call Ice 1. But under extreme pressures, like those found deep within icy moons or large dwarf planets, water can be crushed into exotic high-pressure phases with names like Ice 2, Ice 5, or Ice 6. These ices have different crystalline lattices, and they absorb infrared light in distinctly different ways. Could the surface of Eris, or a layer just beneath it, contain traces of these exotic high-pressure forms? It is a startling possibility. Such phases typically require immense pressure to form, conditions usually associated with deep interiors. For them to influence the surface spectrum, there would need to be a mechanism to transport this material upward. This could point to geological activity powerful enough to dredge up material from deep within the mantle, or it could suggest that the entire icy shell has been subjected to global pressures we have not accounted for, perhaps from the sheer weight of overlying ice or from ancient tectonic forces. Another explanation lies in the intimate mixture of different ices. Methane ice on Eris is not sitting in pure, separate patches. It is likely intimately mixed with nitrogen, water ice, and those complex organic tholins in a frozen granular matrix. The way these components interact at the microscopic level can shift their absorption signatures. The extreme cold itself alters the physics. At temperatures so close to absolute zero, molecular vibrations slow, and the infrared fingerprint of a molecule can change in subtle ways our room temperature lab experiments fail to capture. Even the size and shape of the ice grains could be a factor. Are they large crystalline chunks or a fine frost-like powder? Each configuration scatters and absorbs light differently. This anomaly is a technical clue with profound implications. It means that the surface of Eris is not just a simple sheet of frozen gas. It is a complex material, possibly forged under conditions we struggle to simulate. Every attempt to match its infrared signature is like trying to identify a unique type of snow by only having seen rain. The mismatch is a direct message that our understanding of chemistry at the edge of the solar system is incomplete. What we are seeing may be the signature of a world that has processed its ices in ways we are only beginning to imagine, locking the secrets of its interior pressure and history into the very structure of its frozen skin. That infrared mismatch hints at a surface far more complex than it appears, yet when we watch Eris over the years, another contradiction emerges. The 21st and 22nd mysteries are a study in cosmic stillness. Despite its wild orbital temperature swings, observations spanning nearly 2 decades show a surprising, almost eerie consistency. Its overall brightness and spectral signature remain remarkably stable. Where are the dramatic seasonal changes? Where is the patchwork of dark and light terrain that should emerge as ices sublimate from warmer areas and recondense in colder ones? This distant world seems to wear a single, unchanging face. We expect a world with a transient atmosphere to be a canvas of constant change. Consider the simple process of frost forming on a window. It never lays down perfectly evenly. It creates feathers, ferns, and thick patches in the corners. On Eris, the equivalent of that window is a global scale, and the frost is made of methane and nitrogen. As the world swings through perihelion and those ices turn to gas, the sublimation should start in the sunniest spots, perhaps near its equator. This would create temporary dark patches where older, irradiated material is exposed. Then, as the gas migrates and freezes out again on the night side or the poles, it should create brilliant, fresh frost caps. We see this exact process on Pluto, with its distinct bright and dark regions that change over time. Yet Eris shows no such obvious contrast. Its surface appears homogeneous, a uniform, brilliant white with that consistent reddish tint. This lack of strong localized features suggests a refrosting mechanism that is incredibly efficient and global. It is not a patchy frost, but a gentle, all-encompassing snowfall that blankets every mountain and crater equally. How could this happen? One possibility is that the tenuous atmosphere once formed is exceptionally well mixed. Instead of flowing in concentrated winds from warm regions to cold, it might form a uniform, planet-wide haze. Then, when the temperature drops, this entire haze could freeze out simultaneously, snowing microscopic ice crystals uniformly across the entire globe. It would be like a fog that freezes in place, leaving a perfect, even coat. Another, more dynamic idea involves the nature of the ice itself. Perhaps the surface is so porous, like a layer of incredibly fine snow, that any gas produced immediately diffuses down into this icy sponge. It would not travel far horizontally at all, but would instead sink straight down, only to refreeze in the pores just beneath the surface. This would create a vertical exchange, not a horizontal one, preventing the formation of distinct dark and bright regions. The surface would always look freshly powdered because the refreshing is happening internally, in a layer we cannot see. This temporal stability and visual homogeneity are deeply puzzling together. They suggest a world that manages its climate with a quiet, global precision. There is no drama of erupting geysers or shifting ice caps, at least none that we can detect from here. Instead, Eris seems to breathe as a single entity, inhaling and exhaling its atmosphere in a slow, uniform sigh that leaves no visible scar. It maintains its pristine complexion not through violent geology, but through a pervasive, gentle process that treats every inch of its surface exactly the same. This quiet consistency is in its own way more mysterious than dramatic change. It means we are not looking at a world of weather, but a world of climate, a deeply integrated system whose secrets are locked in the microscopic structure of its ice and the ghostly flow of its vanishing air. But that uniform, silent face masks a hidden gravitational power. Eris is not just a passive wanderer in the dark, it is a massive anchor whose influence may stretch far beyond its own moon. This 23rd mystery examines its potential role as a gravitational conductor, subtly orchestrating the movements of smaller, unseen neighbors. Could Eris, the largest known resident of the scattered disk, act as a resonant perturbing body, shaping the stability and distribution of other objects in its remote neighborhood? The concept of orbital resonance is a cosmic melody. It occurs when two orbiting bodies exert a regular, periodic gravitational influence on each other, often because their orbital periods are in a simple ratio like 2:1 or 3:2. This creates a repeating pattern of nudges that can either stabilize an orbit or destabilize it, depending on the rhythm. Neptune is a master of this, locking many Plutinos, including Pluto itself, into a stable 2-3 resonance that protects them from close encounters. Eris, with its substantial mass and unique, highly inclined orbit, might be performing a similar, though far more subtle, symphony in the scattered disk. Its immense distance makes direct, strong resonances with inner solar system objects unlikely. However, its gravitational field is a vast, invisible web. As it moves along its tilted path, its pull could be shepherding a population of smaller, icy bodies that share similar orbital characteristics. These objects would not be in a tight, clockwork resonance like Pluto and Neptune, but in a looser, longer-term dynamical relationship. Eris's gravity could be acting as a stabilizing shepherd, preventing these smaller bodies from being ejected entirely or from drifting into orbits that would bring them too close to Neptune. In essence, Eris might be the gravitational cornerstone of its own little corner of the scattered disk, a distant king whose presence defines the court around it. The alternative is a more chaotic influence. Given its eccentric orbit, Eris's gravitational pull varies dramatically as it swings from aphelion to perihelion. This changing tide could actually destabilize certain orbits, acting as a periodic disruptor that occasionally scatters smaller objects, sending them on new journeys inward toward the giant planets or outward into the Oort cloud. This would make Eris not a stabilizer but an agent of slow, cosmic chaos. Detecting this influence is a monumental challenge. The objects in question are faint, small, and incredibly far away. Finding enough of them and mapping their precise orbits over decades is the only way to see the ghostly hand of Eris in their motions. If a pattern emerges, if a cluster of these distant objects share orbital elements that seem to dance to the same slow, inclined tune as Eris, it would be a revelation. It would mean Eris is not an isolated oddity, but the central figure in a hidden population, a gravitational lighthouse whose beam, though faint, guides other travelers in the perpetual night. This potential role redefines our view of the solar system's frontier. It is not a formless, random cloud of debris. It may be structured with invisible lines of gravitational force connecting worlds across billions of miles. Eris, in its silent journey, may be drawing maps in the dark, its mass writing rules for a kingdom we are only beginning to perceive. The quiet gravitational influence of Eris may write rules for distant neighbors, but the dance of its own moon holds a final, critical clue. Our 24th mystery focuses on a subtle but profound detail of that dance, the unexplained tilt of Dysnomia's orbit. We know Dysnomia travels around Eris in what appears to be a nearly circular path. Yet the most important question about its orbit remains unanswered. Is Dysnomia's orbital plane aligned neatly with the equator of Eris, or is it significantly tilted? This single piece of missing information is a master key to unlocking the system's history. If dysnomia orbits directly above Eris's equator, it suggests a relatively quiet and orderly past. A moon forming from a disk of debris left by a giant impact like our own moon would naturally settle into an equatorial orbit. It would also indicate that tidal forces have had ample time to circularize and align the orbit, a sign of an ancient, settled system. A tilted orbit, however, tells a story of profound disturbance. Imagine a spinning top with a hoop around its middle. Now, imagine that hoop is suddenly knocked askew. That is what a tilted lunar orbit represents, a sign that something powerful knocked the system off its original axis after dysnomia formed. What force could achieve such a thing? One possibility is a close gravitational encounter with another large body, perhaps even the hypothetical planet 9, whose distant tug could have torqued the entire Eris dysnomia system, tilting the moon's path without breaking the bond. Another, more dramatic possibility is that dysnomia itself is a captured object, a wanderer that Eris grabbed from a different plane of motion. Its orbit would then be a fossil of that ancient capture event, forever angled relative to its captor's spin. The tilt, or lack of it, also directly controls the tidal evolution of the pair. Tidal forces are strongest when a moon orbits in the equatorial plane of its planet. If dysnomia's orbit is tilted, those forces are weaker and work differently, dramatically slowing the process of circularizing the orbit and synchronizing rotations. This could explain why Eris spins so slowly and why dysnomia may not be tidally locked. A tilted orbit means their gravitational embrace is an awkward, inefficient one, generating less internal heat and taking far longer to settle into a final, locked state. In essence, the unknown inclination of dysnomia's orbit is the final parameter in the equation of their shared life. It determines how much heat they have generated for each other over billions of years, whether that heat could maintain a subsurface ocean, and what violent or gentle forces shaped their lonely corner of the solar system. Until we can measure this angle with precision, perhaps with a visiting spacecraft, the full story of Eris and its dark companion remains frustratingly out of focus, a cosmic dance whose most fundamental step is still a mystery. The final and perhaps greatest mystery pulls all the threads together, asking a single, fundamental question: what is the ultimate source of Eris's internal heat? Every clue we have explored, from its brilliant surface to its potential subsurface ocean, points to a world that is not entirely frozen solid inside. Yet at its unimaginable distance, the sun is powerless to generate and retain the warmth necessary for any form of geological activity. Eris must rely on its own hidden engines. The most straightforward answer is radioactive decay. Deep within its dense, rocky core, elements like uranium, thorium, and potassium have been steadily breaking down for over 4 billion years, releasing a slow, persistent trickle of heat. In a world insulated by a thick shell of water ice, this radiogenic warmth could be enough to maintain a layer of liquid at the core mantle boundary, or to soften the ice just enough to allow for slow convection. But is it sufficient? Some models suggest that for a body of Eris's size and composition, radioactive decay alone might only provide a faint whisper of warmth, barely enough to keep the deep interior from becoming completely rigid over such vast timescales. This forces us to consider other, more dynamic sources. Could tidal heating from its moon dysnomia provide the critical boost? The gravitational tug of war between the two bodies, flexing their interiors, generates friction. While this process is often potent for moons orbiting giant planets, the tidal forces between Eris and its much smaller companion are far weaker. For tidal heating to be significant, their relationship would need to be in a state of ongoing dynamical tension, perhaps with dysnomia's orbit still circularizing or with an unusual orbital tilt creating constant, inefficient flexing. It is a subtle, slow cooker method, but over billions of years, even a tiny trickle of energy can accumulate into a substantial thermal reservoir. There is also the lingering heat of accretion and collision. The energy released when Eris first formed from countless smaller bodies, and the colossal impact that likely created dysnomia, injected a staggering amount of primordial heat into its interior. A world of its size and density would be exceptionally good at trapping that initial furnace-like warmth, letting it dissipate with agonizing slowness across the eons. This is not just leftover warmth, it is the fading echo of its own violent birth, still perhaps providing a gentle simmer beneath the ice. The true answer likely lies in a combination of all these sources. Radioactive decay provides the baseline, the steady heartbeat. Tidal forces, however minor, add a rhythmic pulse, and the primordial heat acts as a foundational warmth, the deep-seated ember upon which everything else sits. Together, they may create just enough energy to power a delicate, slow-motion geology. This internal heat is the master key that could unlock every other mystery. It is the engine that could drive cryovolcanism to refresh the surface, the power that could maintain a subsurface ocean's liquidity, and the force that could enable the chemical cycles that produce its strange, uniform coloration. It transforms Eris from a simple, frozen relic into a complex, layered world with a hidden, dynamic heart. Yet we are left at the very edge of our knowledge, looking across billions of miles of darkness at a point of light. We have assembled the clues from the faint whispers of reflected light and gravitational wobbles, but the final proof, the definitive measurement of its warmth, remains out of reach. The ultimate source of Eris's heat is more than a scientific question. It is a test of our understanding of what is possible in the cold, dark frontiers of planetary systems. It asks us how life, in the broadest geological sense, can cling to existence in the most hostile of environments, powered by nothing but its own ancient fires. Solving these 25 enigmas demands more than distant observations. It requires a journey of staggering ambition, a voyage to the scattered disk itself. This is the Great Exploration Challenge, a mission profile that pushes the very limits of human engineering and patience. To send a probe to Eris is to commit to a timeline measured in human lifetimes. Even with the most advanced propulsion we can currently envision, a direct flight would take over 25 years. A gravity assist from Jupiter could shorten that, but it would still be a multi-decade odyssey. The spacecraft would need to be a paragon of reliability, carrying its own nuclear power source and sophisticated autonomous systems, for radio signals would take hours to reach it from Earth. It is a testament to our desire to know, to send a piece of our curiosity on a one-way trip that may not yield answers until the scientists who designed it have grown old or passed away. Yet the prize is worth the patience, a flyby mission screaming past Eris at tens of thousands of miles per hour would revolutionize our understanding. Its instruments would need to capture a flood of critical data in a fleeting encounter. First and foremost, high-resolution cameras would map the surface in exquisite detail, searching for those sublimation pits, potential geysers, or tectonic fractures. Is the surface truly uniform, or does it hide a complex geology under that bright sheen? A precise measurement of its shape would settle the density paradox and reveal if it has the equatorial bulge of a differentiated world with a subsurface ocean. Spectrometers would perform a chemical biopsy, analyzing the surface ices to finally decode the infrared mismatch and quantify the exact mix of methane, nitrogen, and complex organics. They would hunt for fresh frosts and exposed material, directly testing the surface renewal hypothesis, but a flyby's glimpse is brief. The ultimate dream is an orbiter, a craft that could break and enter into a long-term dance with the dwarf planet. From orbit, it could map the entire surface in all wavelengths, monitor seasonal changes over years, and precisely measure the gravitational tugs that reveal the internal structure layer by layer. It could determine the exact tilt of Dysnomia's orbit, measure the moon's composition, and study their gravitational interplay to calculate the tidal heating at work. It could even attempt to directly sample the tenuous atmosphere during a hypothetical perihelion passage, analyzing its composition and pressure in real time. Each measurement would be a key turning in the lock of these 25 mysteries. Eris is more than a distant curiosity. It is the ultimate prize for understanding the formation of the outer solar system. As the largest known object in the scattered disk, it is a preserved planetary embryo, a building block of a world that never was. Its composition, its orbit, and its very existence hold clues to the gravitational storms that racked our solar system's infancy and shaped the architecture we see today. To explore Eris is to read a chapter of our own cosmic history written in ice and rock at the very edge of the sun's influence. The data returned would not just solve puzzles, it would rewrite textbooks. It would tell us how common such hidden oceans might be in the dark, what forces truly sculpt the orbits of distant worlds, and whether the bright, lonely sentinels of the deep freeze are silent tombs or worlds with secret, slumbering hearts. The mission is a monumental challenge, a conversation across generations, but the voice answering from the dark could change our story forever. Eris stands as a permanent monument to our evolving understanding of the cosmos. It is far more than just the largest known object in the scattered disk. This distant world became the catalyst, the single celestial body whose discovery forced humanity to collectively look at our solar system and ask a foundational question: what is a planet? The debate it ignited was not mere academic squabbling. It was a necessary revolution in how we categorize our cosmic neighborhood, a recognition that nature is far more diverse and wondrous than our old labels could contain. Through that controversy, Eris taught us that definitions must serve discovery, not limit it. The journey through its 25 mysteries has painted a portrait of a world of profound extremes and tantalizing potential. We have traced its wildly tilted and elongated path, a gravitational fossil of the solar system's violent youth. We have marveled at its brilliant, mirror-like surface, a paradox of pristine ice in an environment that should have darkened it eons ago. And we have pondered the most thrilling possibility of all, that beneath that frozen crust, a global ocean of liquid water might persist, kept warm by the slow decay of radioactive elements and the gentle kneading of tidal forces. Each mystery, from its missing nitrogen to the darkness of its moon Dysnomia, interlinks to form a story that is still being written. Eris challenges our assumptions about geological activity, atmospheric dynamics, and the very ingredients that make a world complex. It proves that distance and cold are not synonyms for death, but can be the architects of strange and persistent forms of planetary life. The greatest takeaway is a humbling and exhilarating one. The most profound mysteries of our own solar system do not necessarily lie in the bright, familiar realms of the inner planets. They are waiting, frozen in time and space, at the absolute edges of the sun's influence in the perpetual twilight of the scattered disk. Eris is a sentinel there, a keeper of secrets about our origins and the potential for hidden habitats in the dark. Its story is unfinished, and it beckons to the next generation of explorers, both with telescopes and with spacecraft yet to be designed. What do you believe is the ultimate truth hidden within its icy heart? Share your thoughts and boldest speculations in the comments below. If you found this journey to the edge of understanding compelling, please like this video and subscribe for more deep dives into the universe's greatest enigmas. Our exploration of the cosmos has only just begun, and the next great discovery is always waiting just beyond